Today we're going to do a continuation of the solubility product and solubility that we talked about in the previous lecture titled Solubility Product. So we've talked about already with acids and bases, like what when we were talking about buffers, that you had the acid present initially and you had your conjugate base present initially as a salt, and that affected what the pH would be at equilibrium. Well, the same thing happens with solubility, is that if one of the ions that makes up part of the insoluble salt is present initially, that's going to affect the solubility of the substance. So that's what we're going to talk about, is common ion effect. We're going to talk about pH. We are going to skip complex ion formation, and then we'll talk about factors that affect solubility like heat. So that's the focus of today's lecture, and hopefully that finishes up chapter 17. So again, we've looked at these reactions already, but let me just again refresh your memory here about the in order to do any equilibrium problem, the first thing you want to do is write down the balanced chemical equation. So we have silver chloride solid, and it's going to be in equilibrium with the silver ion aqueous and the chloride ion aqueous. So when we write the expression for that, we get this. And this particular expression is called a solubility product expression. It's not a Ka or Kb or a Kw. It's called a solubility product expression. So we find the solubility product constant in a table where it's given in the problem. And this is generally at 25 degrees Celsius, unless otherwise stated, because temperature does affect solubility. And then we've learned to do an ice table where S of this is generated when this dissolves, and S of this is generated, so we get S squared. It's because S times S, S squared. We set that equal to solubility product, and we solve for S. And that is the molar solubility of the silver ion, the molar solubility of the chloride ion, and it's the solubility of silver chloride because that's where this ion came from. It's a one-to-one relationship between silver and silver chloride. So that is the solubility, molar solubility of the silver chloride. That's what we did actually in the last lecture. But what would happen if I added some silver nitrate to the solution? So not only do I just have water and silver chloride, but I add some silver nitrate. Now we know silver nitrate's water soluble, and if you don't know that silver nitrate's water soluble, you got to go back and look at the solubility rules in chapter 4. But when I add solid silver nitrate to this solution, it dissociates into silver ions aqueous and nitrate ions aqueous. So we have silver ion that's going to be generated by the silver chloride, but we also have silver ion present from the silver nitrate. And so this is going to be called the common ion effect. So what they're saying is the silver ion does not equal the chloride ion concentration, because normally what we saw was silver chloride dissociates into a silver ion and a chloride ion, and these are both of the same concentration because they came from the same source. But this case, we're adding silver ion through silver nitrate, so this concentration will be greater than the chloride ion concentration. All they say it's not equal to right there. So the question is, the silver ion will be equal to 0.1 molar plus the silver ion contributed by the silver chloride. So we want to see how that affects solubility and solubility. So let's look at the next question. All right, so the equilibrium expression is now the solubility product the silver ion concentration is the 0.1 molar silver nitrate that we added, plus the solubility of the silver chloride, times the solubility of the chloride ion. So this would be kind of complex. This would start a quadratic, but we're going to assume, because this number is so small, and that's generally going to be the case, that x is negligible, or that S is negligible. So that's going to be equal to 0.1 molar for the concentration of the silver ion. So now what we have is 0.1 molar times S. We get 0.10 or 0.10 molar times S. We solve for S, and now the solubility is, the molar solubility is 1.6 times 10 to the -9th. So the amount of silver chloride that can dissociate or dissolve is significantly less than if we just had pure silver chloride in water. So let's compare this. If you go back, if there's nothing but silver chloride in water, the solubility is 1.3 times 10 to the -5th. But once we add a common ion, the silver ion through silver nitrate, and we have an initial concentration of silver ion, 0.10 molar, the solubility is 1.6 times 10 to the -9th. That's a difference of about 10 to the 4th, right? And that's a 10,000 time difference. So common ion effect definitely suppresses how much silver ion is going to be dissolved. Or silver chloride is going to be dissolved. Let's say it that way. Silver chloride is going to be dissolved. All right, so let's have you try a problem on your own. It says calculate the molar solubility of silver chloride in a solution that is 6.5 times 10 to the -3 molar in silver nitrate. So what that is saying is that silver nitrate is AgNO3. All right. We know this dissolves in water. So whatever this concentration is for silver nitrate, and since it's a 1-to-1 relationship between silver nitrate and the silver ion, that is the concentration initially of the silver ion. So you write a balanced chemical equation. You write the solubility product expression. Here it is. You write an ice table. We've done this over and over. This is integrated into the constant itself because its concentration is not going to change appreciably. What's different about the problem we're doing here is you initially have a concentration of silver ion, and the initial concentration of the chloride ion is 0. So the change, because this was initially 0, we know that Q is less than K initially. The reaction is going to go in the forward direction. So we're going to gain S amount of the silver ion and S amount of the chloride ion. We add these together, we get the equilibrium values for this. We're going to take those equilibrium values and plug them into the equilibrium expression. And so when we do that, we get this. We're going to assume that this X is negligible. That makes it much easier for us. Solve for S. We get S equals 2.5 times 10 to the -8. So right here it says the presence of silver nitrate reduces the solubility of silver chloride by approximately 500. So a big change, That's what the common ion effect does. We saw it suppress the amount of acid that becomes, that dissociates or ionizes when we talked about acids and bases. And now we're seeing where it suppresses the amount of silver chloride that's going to be dissolved. So common ion effect, we saw it both in buffer systems and solubility systems. All right, let's talk about pH. So the solubility of a substance also can depend on the pH of the solution. So insoluble bases tend to dissolve in acidic solutions, while insoluble acids tend to dissolve in basic solutions. So here we have magnesium hydroxide. That is the component of milk of magnesia. This stuff doesn't dissolve very well in water. In fact, there's the solubility product for it. Look how small the number is here. And so if I'm going to solve for this, if I'm going to do an ice table, I'm going to gain, these were initially 0. I'm going to gain plus S amount of this, and I'm going to gain plus 2S amount of this because the coefficient here is 2. I plug that into the expression, which is magnesium 2S raised to the second power here. And I'm going to solve for S. So 2S raised to the second power is 4S squared. 4S squared times S is 4S cubed. So I have 4S cubed equal to the solubility product. And so I take the cube root of both sides, and I find out the solubility of magnesium hydroxide is 1.4 times 10 to the negative fourth. Because again, it's a one-to-one relationship between S and magnesium hydroxide. So you say, well, that's not very good. That's 1.4 times 10 to the negative fourth molar. So what happens if I add acid to this solution? And the same thing, when we drink milk of magnesia, it's going to react with the acid in our stomachs. So there's your real-world application. Well, actually, before they do that, they want you to calculate the pH. So if the pH is, the solubility was 1.4 times 10 to the negative fourth. We multiply it by 2 because for every 1 milk of magnesia, or just magnesium hydroxide, we get 2 moles of hydroxide. So this is the concentration of the hydroxide. We take the negative log of that, we get a pOH of 3.55, and then you got to subtract that from 14 to get the pH. So the pH of this solution is 10.45. It's a basic solution. And we expect it to be a basic solution because this is a base up here. In a solution with a pH less of 10.45, like your stomach, the solubility of magnesium with hydroxide would increase. There's a typo here. There should be a little subscript 2, right? All right, let's prove it. All right, so we're going to add hydronium ion, like stomach acid, to, which is mostly HCl. We're going to add that to this reaction. So here's what's going to happen. The hydronium ion from the acid is going to react with the hydroxide ion to make base. And we're going to make this a coefficient of 2 and a coefficient of 2 here, so it cancels out with all the hydroxide here. That's why there's a 2 here instead of a 1 and a 2 here, and that's why it's 4 waters here. So when I add these two reactions together, this is what I get overall. Magnesium hydroxide, milk of magnesia, reacts with the stomach acid to form magnesium 2 positive and 4 waters. So notice we've neutralized the acid in the stomach, and the other thing is we've generated water, and you're going to find magnesium tends to cause, if you're constipated, this is what loosens that up and flushes it out of your system. All right, so that's why people take milk of magnesia, either for upset stomach, which may be too much acid in the stomach, or they're constipated and they drink some milk of magnesia and they find that that helps relieve that. So if the pH is greater than 10.45, then the hydroxide ion concentration would be higher and the solubility of magnesium hydroxide would decrease, but because of the common ion of the hydroxide ion. So if it's greater than 10.5, that means, which we calculated if it was pure magnesium hydroxide and water, if it's greater than that, it means we have a greater concentration of the hydroxide ion, and the common ion would suppress this from happening, from it dissolving, and we would have less of this would dissolve. But if we add an acid, if we have a pH less than 10.45, then the acid's going to react with the hydroxide, consume it, and the reaction's going to shift to the right. We're going to form more magnesium. Well, let's do up here. Let's do this. We're shifting this reaction to the right, because as we take this away, this has to be made up, and so more magnesium hydroxide is going to have to dissolve to make up for the loss of the hydroxide ion by the acid. So that's how insoluble salts that are basic dissolve in water, by adding more, by making the solution acidic. You dissolve more of the solid to make up for the loss of the hydroxide ion that reacted with the hydronium ion. All right, so let's look at this example. So here we have barium fluoride. It's a solid, and it dissolves into barium ions and 2 fluoride ions. And here's the solubility product for it. So if I add hydronium ion in an acidic medium, the hydronium ion is going to react with the fluoride ion, and it's going to form HF. All right. So let's just look. Actually, I jumped the gun here. Let's just look at this. HF, we know, is that a strong acid or a weak acid? You have to know this. It's a weak acid. It's not one of the 7 strong acids. And so the process of HF ionizing is HF, hydrofluoric acid reacts with water to form the hydronium ion and the fluoride ion. So what happens when we add acid to this? Well, let's look at it. So let's write it as 2 steps. Here is our barium fluoride dissolving into or dissociating into barium 2 positive and 2 fluoride ions. And again, we're going to say 2 moles of hydronium ion reacts with 2 moles of fluoride ion to form 2 moles of hydrofluoric acid plus 2 moles of water. Why did we do 2? Because we want this to completely cancel out there. When we add this together, we get this equation. All right? So we have barium fluoride reacts with the hydronium ion that forms barium ions, 2 moles of hydrofluoric acid, and 2 moles of water. And then you could solve this as a solubility product, right? You could do that, but you can see what happens is the more acid I add, the more fluoride ion that's consumed, the more the reaction has to shift to the right to make up for the loss of the barium fluoride. And therefore we see solubility. We see more barium fluoride dissolve. All right, so here's what it says. The solubilities of salts containing anions that do not hydrolyze, such as chlorine, bromine, and nitrate, are unaffected by pH. But if the ion, like the fluoride ion, is the conjugate base of the weak acid, HF, then by adding acid, we are going to consume the fluoride ion, which causes more of the salt to dissolve. But if the salt contains, if the conjugate base is if the conjugate base is from the strong acid like HCl, then we know that chloride ion is not going to react with hydrogen ion and form hydrochloric acid. That reaction does not happen because hydrochloric acid is a strong acid. So that's what they're saying. The conjugate bases of strong acids do not undergo do not hydrolyze, and so pH does not affect the solubility of those ions. It's a good problem. Good problem. All right, let's put it all together. Let's look at one here. So it says, which of the following compounds will be more soluble in acidic solution? So the first thing you write is the solubility expression, the solubility of in this case, copper 2 sulfide. You hone in on this part here, and you go, if I add an acid to this, and I look at its conjugate acid, I would get this, right? Is that a strong acid or a weak acid? So that tells us that yes, this is going to happen. If I add hydrogen ion or hydronium ion, it is going to react with the sulfur and form this and this. So in this case, by adding acid to this copper 2 sulfate solution, it is going to cause the loss of the sulfide ion. So this decreases in concentration, and the reaction has to shift in such a way as to make up for that decrease. And so copper 2 sulfide will dissolve better in an acidic solution. All right, let's look at silver chloride. So silver chloride dissociates or dissolves into these 2 ions. If I add acid, Will the acid react with the chloride ion and form HCl? No, HCl is a strong acid. This chloride ion does not react with the hydronium ion. Therefore, adding acid does not affect the pH, does not affect the solubility of the silver chlorides. Why? Again, because the hydrogen ion does not reduce the concentration of the chloride by forming hydrochloric acid. That does not happen. Therefore, the hydrogen ion does not affect the chloride ion concentration, and therefore this reaction does not have to shift to the right to make up for the loss of the chloride ion. All right, next one, lead 2 sulfate. All right, so here's our solubility equation. If acid is added to this, will it stick to the sulfate? Yes, it does. This is a fairly strong conjugate base because HSO4 negative is a weak acid. So yes, this will donate a hydrogen ion to this and form the hydrogen sulfate ion in water. So if I add acid to lead 2 sulfate, it will cause more of the lead to dissolve because we're going to decrease the concentration of the sulfate ion, and so the reaction has to produce more. It has to shift in such a way as to make up for that loss. This is Le Chatelier's principle, if you want to really think about it that way. You say, why do I need to know this stuff? This is kind of what was going on in, I don't know if it was lead 2 sulfate, but there was a lead compound in Flint, Michigan that was coating, they had lead pipes, right? Lead drinking water pipes seems crazy today, but they put conditioners in the water so that the lead would not dissolve into the water, so people weren't drinking lead ions in their water. But when they cut costs, they stopped putting the conditioner in there. And so then the coating, and I don't know if it was lead 2 sulfate or some other coating that was inside the pipe, starts to dissolve into the water. And now that increases the lead concentration in the water. And that's what causes exposure to the lead ion in the drinking water. So before there was a coating here, over time there's a coating between the lead pipe and the water that's flowing through it. But once they changed what was going on in the water, the additive they added to the water, then the lead started leaching out because this substance was being consumed, and that caused this to be formed. And again, I don't know if it was lead sulfate or some other lead compound. Could have been lead oxide maybe or something like that. So good question. Good one that I want you to be able to do. That's an important one. I'm going to skip over a complex ion. Could be covered. I think there's more important things to cover this semester, so we will skip over this. All right, fractional precipitation qualitative analysis. We're not doing this as well, so we're skipping over that. And we're skipping over the qualitative analysis. We used to do this in lab, and we haven't done it for a number of years, so I don't think it's worth covering. So that finishes up Chapter 17. It's a little short video here. But that's all the videos for Chapter 17, and we will start. We're really changing gears. Next, we're going to start talking about thermodynamics. So this is the conclusion of, let's just kind of draw these out again. What is this all about? Chapters 15 through 17. It's all about equilibrium constant and constant expressions. We've talked about Kc, we've talked about Kp, we've talked about Kw, we've talked about Ka, we've talked about Kb, we've talked about Ksp, Ksp, solubility product. It's all about K. It's all about using ice tables. It's talking about common ion effect, whether it was buffers or solubility. And then we've also talked about titrations, how to do a titration. So hopefully the titration lecture help you with the lab that you're doing. So that's where we'll stop at, and the next information will be about thermo.